Okay, this one is on moving control volumes. So up till now we've considered this region we've focused in on, and that control volume stays fixed, and fluid comes in and out, and maybe momentum gets stored in that region, or maybe not, uh, and things like that go on. But sometimes your object will be moving, so picture a jet squirting some sort of cart that will do problems like that. And what are the forces in that case? Well, it makes more sense to somehow attach the control volume to the object of interest and have it follow it. And so that introduces this idea that the control volume is moving. And so this is Reynolds transport theorem with a moving control volume. And the direct attack on this is intricate. So if we were to take that same approach where we derive Reynolds transport theorem and we say that this is the system at t equal to 0 and it's equal to the control volume at t equals 0. And if we assume that there's some sort of flow through this region, and it takes the fluid that was inside the control volume out, and so this would be the system at t equals delta t. So a little while later the fluid gets pushed out by the flow. That gave us the Reynolds transport theorem as we have it now. We need to add to this saying that, you know what, that control volume might do something else, and this might be the control volume at t equals delta t. And so if you recall those flux terms where we had to kind of calculate the B stuff that ended up in this part of the system that came out and over here, it's even more intricate and distasteful to try to figure it out when the control volume is also moving. And the direct approach isn't illuminating, and the full formula is fortunately, though, rather unnecessary for many cases. Turns out it gets a lot easier if we focus in on one specific case, but it's a specific case of high value. And so what we're going to assume is that the velocity of the control volume is equal to a constant. So the entire control volume may be moving, but let's say it's moving at a constant velocity, which implies that there's no shape change. It starts out in some shape, whatever we drew around our object of interest, and it stays that way. And what that allows us to do is then follow the control volume, switch to a frame that tracks it, and it recovers the problem as we had it before, though there are a couple of issues we need to deal with. And so when we talk about changing frames, we talk about moving our velocities. We're going to find a new velocity, w, which is equal to our old velocity minus the velocity of the control volume. And if we're in a frame moving with the object and we do that same Reynolds transport theorem analysis here, the black and the blue would stay under the black up here. The control volume would stay in place because we're just tracking it. The velocities would just be this, and we would come up with a Reynolds transport theorem as before with one minor change. Equal. So for general B stuff, control surface, B stuff, and we end up with W dot N dA. So this is the change. Now W relative to the control volume. Now I want to consider this into forms as we use it for a problem. So I'm going to start looking at momentum, and then I'll show you that if we invoke conservation of mass, something interesting and useful comes out of that. And when I say interesting is relative. So momentum. B is equal to velocity. We don't get to just say momentum's in one frame or another frame at this point. We derive this before B stuff, we were following this volume, but this was the amount of momentum that was in B before, and it's still the amount of momentum in B. And we're going to assume one other thing. So we're going to take that, we're going to assume steady. So we're steadily following the control volume in this frame. And it's not accumulating mass or momentum or any sort of B stuff inside of it. So a lot of our problems, as you know, are steady problems. So what's left? Well, you get sum of the forces. That's what the dB cis dt is. And that's equal to the integration of the control surface rho velocity w dot n dA. So that's just going up to this expression, keeping the non-zero terms and putting in velocity for the B stuff. The next step, what I want to do is say, you know what, this is really kind of confusing. I have two different velocities. Well, it turns out that the difference makes no contribution. I'll show you why. So what I'm going to do is say this. I'm going to say this V is equal to W plus V control volume. So I just go back up to this definition of this frame change and replace that V with that. And it gives us two intervals then. So the sum of the forces is equal to control surface rho V control volume W dot N dA plus control surface rho W dot N dA. This first one, well, it can be written like this, that since that volume is constant, that can come out, and we can say control surface rho W dot N dA. And it turns out this is 0, and I can show you why this is 0 by going back up to this expression. This was general for whatever B stuff we want, and say rather than write it for momentum, let's write it for mass. So this term's 0. We're still steady. There's no storage of mass. Little b becomes 1 when you deal with mass. And dB cis dt is 0. You don't create or destroy mass. And so 0 is equal to control surface rho W dot N dA. That was just invoking this one for mass. And you see something immediately is that these are the same. That's equal to 0. Therefore, that's equal to 0. Therefore, this first term up here is equal to 0. And we get our final result. Which is that. Now there's only one velocity we need to use. We just use velocities relative to the control volume. So it simplifies. Now this isn't wrong up here. If you do this correctly, you should get 0 contribution for this different term. This one's just simpler to use because you just say all my velocities are relative to the control volume. That's what I'm going to use. And you can then get your sum of the forces, or however you need to use this expression. And so we'll do examples with this and show that this is really, in some sense, no harder than before.